All right, let's talk about haloalkanes. Haloalkanes are organic compounds where we have a hydrocarbon group that is bonded to a halogen. They've got the general formula Rx. So the R group stands for an alkyl group and the X is a halogen. And obviously the X could be fluorine, chlorine, bromine, or iodine. Now, these compounds have a bit of a reputation because they used to be used as a propellant in aerosols. So cans of spray paint or deodorant and things like that. And it was found that haloalkanes damage the ozone layer. So quite a number of years ago now, countries around the world got together and decided to limit the use of these compounds. And now the propellant in aerosols is largely other compounds such as hydrocarbons. And this has led to the ozone layer being saved, and actually I think the latest evidence is that it's starting to grow in size again. So naming haloalkanes is quite simple. We just take the stem of the compound and number the halogen as a substituent such that we put the number of that halogen in front of it. And so it's quite simple once you've done naming of any other compounds with substituents. Molecules with other functional groups, normally the other functional groups take precedence over the halogens. So for example, if we have an alcohol, it will be a halo alcohol of some type. So in this case, we've got a cyclohexanol. So there's the stem of the name, cyclohexanol, and we number towards the nearest substituent, which is the halogen in this case. And so this is a 2-chlorocyclohexanol. And similarly, if we have a alkene, then we'll have an ene ending. So this is a cyclohexene, and we number starting with the alkene carbon atom and numbering towards the other alkene carbon atom, and then we'll end up getting to the halogen, in this case on carbon number 4. So this is 4-bromocyclohexene. Now that's the IUPAC rules for naming haloalkanes. The common names for many of these compounds are a little bit different. We name them as an alkyl halide. And so 2-fluorobutane can also be called sec-butyl fluoride. And similarly, a double bond between two carbons like this is commonly called a vinyl group. So this is vinyl chloride, which is a common monomer for making polyvinyl chloride, PVC. Haloforms are a very common halide containing molecule, organic molecule, and they have the general formula CHX3. So if it's a chlorine, then it's chloroform, which by IUPAC nomenclature would be called trichloromethane. And haloforms, particularly chloroform, are very common chemicals, and they used to be used very widely for everything, all sorts of solvent situations, including dry cleaning of clothing. So chloroform was very commonly used, but I think it's largely being phased out because chloroform has fairly nasty sort of properties and is not good for the environment. So haloalkanes are generally synthesized through a halogenation reaction. And this is different to the halogenation of alkenes. This is a replacement of hydrogen atoms via a radical reaction. So we take methane, for example, and we chlorinate it with chlorine in the presence of either light or heat, and we generate chloromethane and one equivalent of hydrogen chloride. Now this is a very vigorous reaction, very strong conditions, and it's difficult to stop the reaction at just one chlorination. So chloromethane, once it's formed, reacts with some of the chlorine as well to generate dichloromethane, and then that reacts with chlorine to generate trichloromethane or chloroform, and finally chloroform can react as well to give carbon tetrachloride. And all of these things will be produced in various quantities depending on the reaction conditions, and industrially the conditions are chosen to favor the particular product that you want to get. And then we can separate the components out of the mixture. And all of these compounds have important industrial uses, although carbon tetrachloride is a very strong ozone depleter, and so there's very stringent regulations around its use, and it's quite difficult to actually source and to use in an organic chemistry lab. So how does this radical chlorination occur, this radical halogenation. Firstly, we have an initiation step where we form two chlorine radicals through either the heat or the light. Okay, once the chlorine radicals are formed, then we have a propagation event. So the chlorine radical reacts with the methane via a mechanism shown here. So we've got single-headed arrows to show a radical mechanism. Don't worry if this isn't familiar to you. We just want to show the overall scheme of this radical process. So that generates hydrogen chloride and a new methyl radical. The methyl radical then in a second step can react with the chlorine, the dichlorine molecule to generate the desired product, the chloromethane, and a chlorine radical, and that goes back into our cycle. And then finally there's termination events. So this is each of these propagation events take radical species and make new radical species. Termination events take two radical species and generate non-radical species. So two chlorine radicals can come together to make dichlorine. A methyl radical can react with a chlorine radical and make chloromethane, or two methyl radicals can come together to make ethane. And so each one of these termination events is going to be happening during the reaction. Let's quickly look at some of the principal reactions of haloalkanes. And they're governed by the properties of these molecules. So haloalkanes have a very polarized carbon-halogen bond. So this here should be the polarized carbon-halogen bond. And so they're readily attacked by nucleophilic species or Lewis bases. So nucleophilic species will generally attack at the carbon bearing the halogen, whereas molecules that want to act as a base rather than a nucleophile, and some molecules can act as both, so we make it a mixture of products. So bases will attack the hydrogen adjacent to that position, make it alkene, and then kick out the leaving group, this bromide. And so we can get substitution and give new molecules like this, or we can get elimination reactions to give alkenes like this. In the nucleophilic substitution, we can use a variety of different nucleophiles. Common nucleophiles are things like hydroxide, alkoxides, so that's where we have an R group attached to oxygen bearing a negative charge. Hydroxide will generate alcohols as the products. Alkoxides will generate ethers as the products. We can take thiolates, which are thiols that have one of the protons removed, and if we use hydrogen sulfide as the precursor, so we have the HS minus anion, they'll react with an alkyl halide to give a thiol. Whereas if we take an anion derived from a thiol, an organic thiol, we'll get this organic thiol here, we'll get a sulfide or a thioether. We can actually take alkyl halides or haloalkanes and react them with halide anions, so we can exchange one halogen for another. So I minus, the iodide anion, can react with a haloalkane to give the alkyl iodide, for example. We can take amines, and they'll react with the alkyl halide to give ammonium salts, and then they will lose a proton to give an amine if we have them in basic conditions. And water can react with alkyl halides or haloalkanes to give initially this sort of species, which can lose a proton and end up giving us an alcohol after proton transfers. And finally, we can use alcohols, and they will react with the haloalkane to give initially this sort of species that then loses a proton via proton transfer to give an ether. So there's a variety of mechanisms by which nucleophilic substitutions can occur. The two most common are what's called the SN2 reaction and the SN1 reaction. So they'll be the topic of another video, but hopefully that gave you a little bit of an outline on what haloalkanes are, how to name them, and some of their key reactions. Thanks for watching.